So lesson 31, we're going to talk about symmetry for geometry, trig here. Basically, symmetry is like when you see yourself in a mirror on the other side. And it says that point A will see itself 5 units on the other side of the mirror at point B. So what we have here then is that points A and B are symmetric about each other about point M, where M is that line of symmetry. So if I actually had a line here, it's kind of like folded in half. You see the same thing on the other side? So it's symmetric about both sides. That distance is 5. They're there. And that's what the paragraph says. So the axis of symmetry is basically the line of symmetry on the bottom that divides a parabola into two congruent halves. So if I even go to graphs now, if I have a parabola, the dotted line there is a line of symmetry. It's symmetric or the same on both sides, yes? And so the axis of symmetry always passes through the vertex. So boom, there's the vertex way down here. And the x-coordinate of the vertex, guys, is the line of symmetry, or the axis of symmetry. So if this point down here happened to be 2, 4, that means x equals 2 is the line of symmetry, or what we call the axis of symmetry. It's what makes it the same on both sides. Okay? That's all things that we probably should know, we've talked about possibly in years past. So how does that all go together? Well, this is how we tell if something is symmetric or not. Now, when I say symmetric, it's on the bottom there. I'll jump to the very, very bottom. Being symmetric is a characteristic of a graph. It's already there. So that means it can be the same on both sides of something. That's different than our next slide where we're going to actually reflect it about something. So symmetric means it's already there. Reflecting means we're actually going to move it or flip it ourselves. Okay? So there's a slight difference. And so, how can I tell if something is symmetric about the y-axis? So if I want to be symmetric about the y-axis, as in here, it says that if I take x out of an equation and replace it with a negative x, the resulting equation is equivalent to the original. So, what does that mean? Let's try that. That means I can take out the x, and I'm going to replace it with negative x. What happens when I square a negative? Makes it positive. So I end up with y equals 2 to the times x squared. Those two equations, here and here, are the exact same. Wait a minute. What is y equals 2x squared? It's a parabola. That's got a vertical stretch of 2, if you guys think of the parent, family, child idea. So it's just a parabola at the center, centered at 0, 0. Is it symmetric about the y-axis? Yes, because this is the y-axis, and it's symmetric. I can rotate it, right, or flip it. It's the same on both sides. It's a little bit tougher now to find a graph that is symmetric about the x-axis. So now we're going to talk about the x-axis. To do that, I would find a parabola that was knocked over. And if you can remember back to your Algebra 2 days, the equation of x equals y squared is a parabola that's laying on its side, right? In this case, to be symmetric about the x-axis, I got to replace the y with a negative y, and then that results in the same equation. Again, using the same thought as we did above, look at what happens when I square y. Here. What happens when I square y? So if I put a negative y or a positive y in, I still end up with y squared. So therefore, I would get the exact same equation without having to show that, right? So therefore, this is symmetric about the x-axis. It's kind of like the x-axis is splitting it in two complete halves. And we have one that is both symmetric about the x-axis and the y-axis. And we would say that would be symmetric about the origin. Okay? Any questions on that? So if you can plug in both of these situations at the same time and end up with the original, therefore it's symmetric about the origin. And again, symmetry is a characteristic of a graph. Characteristic of a graph. You're not doing anything to a graph. You're not changing it. You're looking at it saying, does it have this property? Then therefore it is this. Which is different, as the next slide, talking about reflections. Reflections, guys, is a transformation in which each point of the original figure, sometimes they call the pre-image, has an image that is the same distance from the line of reflection as the original point, but is on the opposite side. Remember that a reflection is what I'm going to call is a flip. I'm flipping it, reflecting it. Okay? So under a reflection, a figure does not change in size. I'm not changing it. Think back to the days when we did our parent, family, child equations. And sometimes, as an example here, we had something like this. Y equals negative 3 times 2 to the x. It's a vertical stretch of 3 because 3 is bigger than 1. But that negative, I told you, did what to the graph? The negative on here reflected it about the x-axis. It didn't change the size or anything. It just took it from opening up to opening down. It reflected it about the x-axis. And how do we end up reflecting it? If I want to reflect something about the y-axis here, I put in a negative x. I put in a negative value. And so what was positive x value now becomes a negative value. If I want to reflect it about the x-axis, which we were doing for our problems over here, I put a negative on outside of the function. Notice that it's getting a little bit crazy with the circle and the square there. But if that square is really on 3 times 2 to the x, if that's the function, I put a negative in it. Now it's not going to be on the top, it's going to be on the bottom. So, let's see if we can come up with an equation for this. Let's try y equals 2x. We all know that if I graph this, or at least I hope, you guys should see something like this, yes? If I want to reflect this about the y-axis, well, the y-axis is here, right? This line. So this point, we're going to say here. If I reflect it about the y-axis, where it has to be where? Where should that point go? To the other side of what? The y-axis. So I would have to take, I'm going to try to color code this, okay? This distance here, right? That distance has to be picked up and moved over here, right? So it has to be moved to the other side. So that means the point is there now. Can that same process be done for this point down here? Yes. That point has to be swung this way to there. So all my points go from a positive x to a negative x. Did it actually affect any of my y values? My y values still stayed positive or negative. Interesting. I just flipped it, everything about the y-axis. So the new graph, if anything, I'll change colors for that, would be the black line, right? But what would the equation look like? Well, y equals a negative of 2x, which is y equals negative 2x. That's a negative slope, right? Instead of a positive slope. So it should be going down. Sorry, I messed that up. Still going to be the same result. This line right here is different. What did I do wrong? It's y-axis. What should I put in? A negative x, right? And what's 2 times negative x? It's a negative 2x. So therefore it goes across the y-axis. The x-axis, guys, we've done that before. We've put a negative out front. That's why our graph's flipped. Instead of being here going up, we went down here, right? That's the parent, family, child stuff that we did with exponential growth graphs. So, what I'm going to do, guys, if you notice, they're a little bit small, I think, on the screen there. You can write this down. This is what we're going to do.
Is this 30 or 31?
This is 31. And what I've got here are 3 different types of graphs, all what I'm going to call the child forms. So guess what we're going to actually do today? Parent, family, child.
So is this still reflection and stuff?
So we're going to translate today, because that's part of this lesson as well. The last lesson where we started parent, family, child was just on graphing an exponential growth or decay graph. This lesson's all about translating any graph. And notice that they're all in the same translating form with an A, an H, and a K. You guys all know what A, H, and K do. We'll go over some of these. We know that A does what? It's a stretch or shrink. Stretch/shrink, right? And tells us if it's reflected. You guys remember that? Yeah. Okay. Reflected about x-axis. We know, I'm not going to write this down, but you guys can, because we have this written down somewhere. How do I know it's a stretch? It's a vertical stretch.
If it's above greater than 1.
What's greater than 1?
A.
A. If A is bigger than 1, it's a vertical stretch. If it's between 0 and 1, it's a shrink. The negative in that would only tell you if it's reflected about the x-axis. Bringing back some memories, huh? What about H?
Wait, so if it's a negative, it's a shrink?
No, if it's negative, that means it's reflected about the x-axis. Doesn't change its size. So it could technically just be a negative 1. It's the same size, just opening down. How about translated? What? H translates
If it's negative half, then it would be a shrink and stretch.
left or right.
If it's negative, yeah. But
If it's a negative 1/2, it's reflected
and a shrink.
and a shrink of half.
So if it's negative like 3, then it's a stretch and then.
Yes. So if it's negative 3, it's a stretch of 3, but reflected about the x-axis. Remember, translated, H is translated left and right, and we probably should put on there, it's the opposite of what you see, right? X plus 2 means you're going 2 to the left. X minus 2 is 2 to the right. So be careful on that. And K, our last component,
Up, down,
is translated
down.
up or down. K is exactly the way you see it. So if I see plus 5 at the end, it goes
Up 5.
up 5. If it's minus 10, it goes
Down 10.
down 10. Okay? So that's all the basic information. We should already know that. We know how to translate graphs if it's in transformational form. Okay? Or what I call that parent or that child form. Here's the thing. I'm going to be able to ask you how to graph any one of these. And you guys can, using my parent, family, child method, if you know the parent. So let's talk about what are the parents of all of these graphs.
X.
So I'm going to pause this for a second. So let's start off with the parents. Let's think of the parents. The first one's a square root. What would be the parent of this square root graph?
X.
Y equals
X. Square root X.
square root of x. I take away all the moving parts. Remember? The a, the h's, the k's. I'm left with y equals a square root of x. Now, we know a parent, but part of this process, guys, was to set up a set of points or things about them that is universal for all parents. And all parents are going to be y equals square root of x. So now, I just need to make a table or a couple set of points. In this case, I'm going to make a table because it's a little easier to organize. But what do we know about square roots?
You guys have plus or minus.
No, plus and minus. If I was solving an equation and I took a square root, then yes, I have to have plus or minus. But not when I'm just graphing. What do we know about square roots? You can't do what?
Oh, subtract, have a negative.
You can't have a negative. So you can't square root a negative number. So do I even have to worry about any negative x value?
Nah.
No. What's the smallest value that I can take a square root of?
0.
0. So guess what I'm going to definitely add in here?
0.
0. What's the next number then? What are you thinking?
1.
1. Next one?
3. 4. 2.
It's 4. I'm skipping. Why would I purposely skip values when taking a square root?
Because square root 2 is not good.
Yeah, square root of 2, it works, but it's not a nice number. What's the next nicest number? When I take a square root? 4 and then 9. That's enough. And here's the cool thing. When I square root them, 0 is
0.
0. Square root of 1 is?
1.
Square root of 4 is?
2.
And
3.
3. Guys, that is your parent for a square root graph. After that, I can multiply my y values by a. I can add or subtract my h values and my k values to my y's. That same process works every time. What about the rational function? Where do you think that one is?
Y equals blank over
Blank over x. What would be left if you took the a away?
A.
A 1.
Wait. This is the parent. Yeah.
This is the parent for the rational function. Hey, wait a minute. We've graphed those before. There's something special about those graphs. They have an,
Twins.
starts with an A.
Asymptote.
That's an asymptote. Where is that asymptote going to be? It's going to be at 0. So it has an asymptote at 0. All of the parents will have an asymptote at 0. Now, wait a minute. We've graphed these before. These ones, guys, take a little bit more training or a little bit more thinking. Because wherever that asymptote, why did I say y equals 0? We also said it has a different one. It's where the bottom equals 0. So all parents will also have an asymptote at x equals 0.
Wait, what?
Because x cannot be 0, otherwise it makes the problem you can't do. But now this is where that thinking comes in. When we establish our asymptotes, especially our vertical ones, it creates us in a predicament where we have to have two t-charts in this one, right? One for the left and one for the right of 0. So, in this one, I still have to do that. I'm not sure. I think this might have been it was on the last quiz, I think.
Do we the left and right one?
So, -1, -2. 1 and 2. Guys, these values will never change. What happens when I put 1 over negative 1? It's negative 1. 1 over negative 2? Negative 1/2. 1 over 1. 1 over 2. Guys, that will be my parent. Then all I have to do is take those 4 points and move them. Stretch them, shrink them, left, right, up, or down. That's all I'd have to do and plot the final results when we get to that child. That's all for the rational function. So let's move to the cube root. What's the parent on the cube root? Y equals? Cube root of x. Now, on this one, I'm also going to make a table of values. And I'm only going to use these 5 values. Just like when we had a square root, we chose perfect squares. When we do cubed roots, I'm going to choose perfect cubes. Here's the thing. Can I take cubed roots of negative numbers?
Nah.
Yes. The cubed root of negative 8 is negative 2. Because remember, a cubed root means what times itself 3 times is that number. And a negative times a negative times positive, but times a negative again is negative. So yes, we can go into the negative territory here. 0, though, is the easiest number to take the cube root of, because the cube root of 0 is 0. What's the next perfect cube? Going positive. It's not 8. No. Universal. 1. Cube root of 1 is 1. Then we go to 8, which is 2. Going in the negative direction. Negative 1, which is negative 1. Negative 8. Negative 2. Those guys are the 3 parents that we are going to deal with this time around. Using parent, family, child. The same process works as it did last time, so let's pick one. Let's do a cubed root graph. So, let's do y equals, let's do 2 times the cubed root of x plus 1 minus 3. We don't have a lot of time, but we got to get through this graph, and then I'll get you your homework. So, what is the parent of this particular graph? Y equals the cubed root of x, yes? So then I go back to my notes and say, hey, what is the point, or what are the points that I want to use for a cubed root? Negative 8, negative 1, 0, 1, and 8. Because you want to see this graph. And the answers to those...
-2, -1, 1.
Yes. Guys, parents will never change. Now, we go to the family. And what's happening? What's my a value?
2.
So it's y equals 2 to the cubed root of x. So that means that 2 does what to my graph? It's a vertical stretch of 2. Yes, guys, you need to have those words on the bridge.
Multiply x by 2?
No, not x. You multiply the y's by 2. So I still get negative 8, negative 1, 0, 1, and 8. That's not changed. But I take all of those y values and make them twice as big. So it becomes negative 4, negative 2, still at 0, 2, and 4. Is everybody seeing that? I just multiply my y values by 2. It's the same process as we've done before. We get to the child, which is
Translate 1 left.
the whole thing. That's the way I ran out of room there. So we're going to say we are translating 1,
Down.
1,
Left.
left. And we're translating 3, down. So, since we're going left, we're going to go left 1. I'm going to subtract 1 from all my x's, so it'll be at -9, -2, -1, 0, and 7. And then we're going to subtract 3 from all my y's because I'm going down 3. So it'll be at -7, -5, -3, -1, and 1. That column is the one, or that T-chart is the one we're going to graph. So our graph will look like this. And I'm going to save myself some space in here. Actually, I need to be up here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And so -9, -7 is way down here. -2, -5, 1, 2, 3, 4, 5 is here. -1, -3. 0, -1. And 7, 1. That is the graph that you need to have. So your homework tonight is for the parent, family, child, these 3 graphs on here. First one is a square root, next one's rational, and the third one is a cube root. Have a great day.